This is a follow-on from a previous video. I'm going through exam style questions. This is question 3. It says 150 gram mass is attached to one end of a light inextensible string and the other end of the string is fixed at a point P as shown in the diagram above. The mass is held at point A so that the string is taut and horizontal. The mass is released so that it moves freely along a circular arc of 250mm radius. When the string moves through the vertical position, the mass is at point B. Neglect the effect of air resistance. Calculate the kinetic energy of the mass. Okay, so a couple of points here. Light inextensible string means that there is no mass from the string. Okay, so we just take the mass to be of the object of 150 grams. One thing we want to do is convert that from 150 grams into kilograms. The other thing to take into effect is we're neglecting air resistance. So as this moves through the air, it's not doing any work to get through that air. There's no frictional force. So in other words, if we want to work out the kinetic energy, we can treat this as an energy problem and look at the energy at this point and the energy at this point. Now the energy at this point is to do with the size of the gravitational potential energy it's being given by raising it up through this height, and then that will all be converted to kinetic energy. So we'll have a loss of gravitational potential energy, a gain in kinetic energy, and there's no other energy loss. Okay, so this question is assuming no air resistance, so no energy loss. Okay, so the other numbers, we've got the radius of this rotation as 250mm, so we can convert that to meters. And what we're suggesting then is at point A, it has gained an amount of energy mgh, and at the end, all that will be converted to kinetic energy, half mv squared. And the mass cancels, and then we've got, oh, that's if we wanted to that's if we wanted to calculate the velocity it was traveling at. Okay, but that's not what we want. We want to actually calculate the kinetic energy. So we actually want to calculate this, but not directly through knowing how fast it's traveling at point B, but just simply because we know that initially came from all the gravitational potential energy. So if we calculate the gravitational potential energy, we know how much energy it has at B. So that would then be a mass of 0.15 kilograms times gravitational field strength of 9.81 newtons per kilogram and a height of 0.25 meters. When you put all those numbers in, you will get an energy of 0.37 joules. Okay, so let me just restate that again. You've given it 0.37 joules of gravitational potential energy. It's then dropped down to this position, so it's dropped down through this vertical height, and we're saying that it's all being converted to kinetic. So however much kinetic energy it has here is equivalent to how much gravitational potential energy it has here. And remember, this is dropped from rest, so it had no kinetic energy to begin with. It was all gravitational potential energy. Right, next then, B says the velocity of the mass. So now we can calculate the velocity. We can do that a number of ways. We can directly say that V is going to equal root 2gh, or we can say that if we know how much energy it's got, using this equation we can rearrange for V. So V would equal twice the kinetic energy divided by the mass, and then that would give us V squared. So if we square root that, we will get the velocity of this mass at point B. So that is 2 times 0.37 divided by a mass of 0.15 kilograms, and then we're going to square root that, and that comes out as 2.2 meters per second. Part C. Centripetal force acting on the mass. Okay, so centripetal force is going to be equal to the mass of the object times the centripetal acceleration, which previously discussed was v squared over r. I know m, I know v, I know r, so I can calculate that. So we've got 0.15 kilograms multiplied by a speed of 2.2 squared divided by the radius, which was 0.25. So that's the radius of this circle. So the circular path has a radius of 0.25. And putting those numbers in comes out as 2.9 newtons. Okay, and then finally the tension in the string. Now you might first think, well, hang on, isn't the tension causing it to move in a circle? Well, that's part of what's acting on the object in terms of forces. Just as a side here, if I say this is the object, yes, there is tension in the rope, which acts towards the center. However, this also has a weight. Okay, it's an amount of mass. So mass times gravity has a force, a weight force, and then that means that the sum of these forces, because the centripetal force will be towards the center, it's going to be T's the larger force minus the weight. Okay, so that's T minus mg, and that is going to be equivalent to, so the sum of these forces, that is going to be equivalent to the centripetal force that's causing acceleration towards the center of the circle. So that is going to be equivalent to mv squared over r. Now, that means then that the tension in the string at the bottom is going to be mv squared over r plus the weight of the object, mg. And we know what the centripetal force was, it was 2.9. And I'm going to add to that the weight of the object, which is 0.15 kilograms of mass times 9.81 newtons per kilogram. And that comes out as a force of 4.4 newtons. And as discussed in an example video, examples of circular motion, we talked about moving in a vertical circle, and the tension in the rope is going to be at a maximum when it gets to the bottom of the rotation, and it's going to be smallest when it's at the top, because at the top the tension and the weight is in the direction of the centripetal force. Okay, so that's 3. Figure 1 shows a fairground ride called a roda. Riders stand on a wooden floor and lean against the cylindrical wall. The fairground ride is rotated. When the ride rotates sufficiently quickly, the wooden floor is lowered. The rider remains pinned against the wall by the effects of the motion. When the speed of rotation is reduced, the rider slides down the wall and lands on the floor. At the instant in figure 2, the ride is rotating quickly enough to hold the rider at a constant height when the floor has been lowered. Draw on figure 2 arrows representing all the forces on the rider when held in this position relative to the wall. Label the arrows clearly to identify all the forces. Okay, first one to do, it's very easy to just label weight acts vertically down. Now, because of this force, it would want to just move down, but it doesn't, so there must be friction opposing the motion down the wall. So there has to be a frictional force. And the only other force then acting, because he's moving in a circle, it means that there has to be a force acting towards the center, and that force is the normal contact force pushing the wall, pushing against him. So that's the normal contact force. Okay, so they're the 3 forces. It says explain why the riders slide down the wall as the ride slows down. Okay, so obviously if he was rotating quick enough, then your centripetal acceleration is great enough to cause enough normal contact to keep you moving in that circle. But what would happen then is, as the ride slows down, the frictional force would reduce. Okay, and at that point then the frictional force, or at some point, would be less than the weight force. And that means that if that force is smaller than that force, there's going to be a resultant vertically downwards. Okay, and so obviously he's going to slip down the slide, down the wall. Okay. Next part. So figure 3 shows the final section of a roller coaster, which ends in a vertical loop. The roller coaster is designed to give the occupants a maximum acceleration of 3g. Cars on the roller coaster descend to the start of a loop and then travel around it as shown. So the direction of travel, it goes around this way and then out. At which one of the positions marked A, B and C on figure 3 would the passengers experience the maximum reaction force exerted by the seat? Circle your answer. So we're talking about the normal contact between the person and the roller coaster cart or the seat. Now, in previous video I did discuss the theory behind this. It's C, and when you think about it, what's happening is at C the speed's going to be greatest, because if you think about the conversion of gravitational potential energy to kinetic energy, that's going to be the greatest conversion. So it's going to be having the most kinetic energy at this point, so it's going to have the largest velocity. And then if we think briefly about the theory at C, you've got the weight of the cart, the person, the weight of the object, and you've got the normal contact. That has to be at its largest because of the fact that the weight is acting exactly opposing in the opposite direction to that. So the sum of these forces is going to be N in the direction of the centripetal force minus W. And that is going to equal mv squared over r. So N is not only going to be the size of the centripetal force, but it's also going to be plus the weight of the person and the cart or whatever you're looking at. So at this point it's going to be, as the question says, the maximum force is going to be exerted at C. And at that point, you're going to feel really pressed into your seat as the normal contact pushes against you. Okay, so you're really wanting to fly off in this direction, and the track itself is pushing on the roller coaster cart. The roller coaster cart's pushing on the seat. The seat's pushing on you, and that's going to be greatest at C. So just summing up, that's the mass times the centripetal acceleration plus the gravitational acceleration. So it's a combination of these two things. At B, the total opposite, that wouldn't be the case. The normal contact and the weight would be in the same direction, so it would be N plus W, and then you would be taking away the weight. So if you're feeling lighter in your seat as opposed to feeling more G's. Right. Finish there and move on to the next questions in the next video.